Welcome to the deep dive. This is where we take a whole heap of information, kind of cut through the noise, and really get to those aha moments for you.
Finding that core insight.
Exactly. And today, we're plunging into a world where, well, precision is absolutely everything. MIG welding.
A fascinating process.
Totally. We're going to unravel the specific parameters that shape the molten metal and explore the really surprising ways that metal actually gets from the wire to the workpiece.
It's not always as simple as it looks.
Not at all. Now, you've given us some fantastic sources, really packed with the secrets to getting that perfect weld. Our mission today is to pull out those essential nuggets for you, give you a crystal clear understanding of these crucial elements.
Yeah, the fundamentals.
Right. We want you to grasp not just the what of these welding principles, but that critical why it matters for getting a flawless, strong connection.
Understanding the why is key.
So get ready to discover the hidden physics controlling what might look like just a simple arc.
That's really where the magic happens, isn't it? What's truly fascinating here is how, subtle tweaks to these parameters, they don't just change a number on a dial. They fundamentally alter the actual physics of the arc.
Oh, okay.
And that leads to vastly different results in the final weld. Understanding these controls is, well, it's just paramount for consistent quality.
Okay, let's dive in then. Let's unpack this by starting with the building blocks, the essential MIG parameters.
The core controls.
Right. And just as a quick refresher for everyone, MIG, or GMA gas metal arc welding, as it's known in the U.S., it's incredibly versatile.
Absolutely. Used everywhere.
You see it on delicate sheet metal, right up to really robust, thick components. At its heart, you've got an arc struck between a continuously fed wire electrode and the piece you're welding.
Melts them both together.
Exactly. Melts both. Forms that weld pool, and it's all meticulously protected from the air by a shielding gas.
That protection is crucial.
And that continuous wire feed, that's its big advantage, isn't it? Makes it super productive, very efficient.
Definitely. For welders, these are the primary variables, the critical controls right at their fingertips.
The levers they pull.
Yeah, think of them as the master levels of the process. Getting them right is, it's the difference between a strong, clean weld and one that's just riddled with problems.
So what's the first lever welders typically reach for? Would that be wire feed speed, WFS?
That's usually the big one, yeah.
It might seem simple, but here's the key insight, right? WFS directly dictates your welding current.
That's the core relationship. Increase the wire feed.
And the current automatically goes up.
Precisely. This direct link means controlling one effectively controls the other. It's the main way you determine how much metal you're actually putting into the weld.
Which affects everything else.
Penetration, bead shape, everything. And you'll typically see standard wire diameters like 0.6, 0.8, 1 millimeter, up to 1.6 millimeter.
Gotcha. And that wire feed speed decision immediately brings us to voltage, doesn't it?
It does. They work hand in hand. If WFS is about how much wire, voltage is primarily controlling the length of your arc.
That glowing space.
Yeah, that gap between the wire tip and the workpiece. This is especially critical in certain modes like spray transfer.
Okay.
In dip transfer, voltage affects how quickly the current builds up during the short circuit and the overall heat input.
So more heat.
Well, increasing both WFS, and therefore current, and voltage will definitely ramp up your heat input significantly.
Right.
And this brings up something important. What about your electrical connections?
Ah, like the cables and clamps.
Exactly. Even slightly loose connections cause a voltage drop right there in the circuit.
Which messes things up.
It throws off the entire characteristic of your welding arc. Visually, think of it like this. Increase your arc voltage, and your weld bead tends to get wider, but shallower. Less penetration.
Okay.
But push it too far, get excessive voltage, and you run into frustrating issues. Porosity, lots of spatter, maybe even undercutting the base metal.
It's amazing how interconnected it all is. One change affects everything. Now let's talk about something that really changes the game. Shielding gases.
Oh, hugely important.
This is where we see that fundamental split, right? The MIG versus MAG name.
Exactly. Two different approaches based on the metal.
So on one side, we have MIG, metal inert gas. That's typically for non-ferrous metals. Think aluminum, nickel, copper.
Right. Materials that react badly with oxygen.
So as the name says, it uses inert gases, pure argon, or sometimes argon-helium mixtures. Why add helium? What's the thinking there?
Helium is interesting. It basically creates a hotter, more uniform arc profile.
Hotter arc.
Yeah, which is really beneficial when you're welding thicker materials or things that conduct heat away really fast, like copper or aluminum. It helps get enough heat in.
Makes sense. Then there's the other side, MIG, metal active gas.
Correct. This is specifically for steels, all grades, including stainless.
Okay.
Here you use active gases. That means small amounts of oxygen, or more commonly carbon dioxide, CO2, are added to the argon.
Inactive means they react.
Exactly. These additions actually react slightly with the molten metal. It sounds counterintuitive, but this provides a more stable arc and ensures really good droplet wetting, how the molten metal flows out.
Fascinating. So the choice of active gas is pretty nuanced too, I bet.
Oh, incredibly nuanced. Take 100% CO2, for example.
Yeah.
It's cheaper, right? And it gives you really good deep penetration.
Sounds good so far.
But here's the catch, the big aha. It fundamentally cannot sustain spray transfer mode.
Really? Why not?
Its ionization potential is just too high. It promotes what's called globular transfer instead, big irregular blobs. That usually means an unstable arc and, well, lots of spatter.
Ah, so cheap, good penetration, but maybe messy and harder to control.
That's the trade-off, exactly. Now, if you blend argon with about 15-20% CO2,
It's a common mix.
very common, you get sort of the best of both worlds, good penetration like CO2, but with a much more stable arc and way less spatter, thanks to the argon.
So the argon helps stabilize it.
Right. Pure argon gives a super stable arc, very low spatter, but the penetration isn't as deep as with CO2. Critically, argon has a much lower ionization potential.
Ah, and that allows
it to sustain that desirable spray transfer, usually above about 24 welding volts.
Okay, and what about for stainless steels? You mentioned specific needs there.
Yeah, for stainless and some low alloy steels, argon with just 1.5% CO2 is common. With austenitic stainless steels, the goal is to keep the oxidizing potential really low, usually 2 to 2.5% CO2 max.
Why so low?
To stabilize the arc without messing up the corrosion resistance of the stainless steel. And because these steels don't conduct heat very well.
Right, low thermal conductivity.
Adding helium, sometimes a lot of helium, like up to 85%, becomes crucial to pump enough heat in and prevent lack of fusion defect.
Wow, 85% helium. So we're talking incredibly specific blends tailored to the material.
Absolutely. And for light alloys, aluminum, magnesium, titanium, copper, nickel, those argon-helium mixtures are often indispensable.
Because of the heat again.
Exactly. Helium's higher thermal conductivity gives you a hotter weld pool. That means better penetration, or you can weld faster.
Sounds like a win-win. Any downsides?
There are trade-offs. High helium content gives deep, broad penetration, which is great, but it also tends to increase spatter. And arc stability can be a bit trickier. Helium raises the arc voltage, so small changes in arc length have a bigger voltage effect.
Yeah.
You also need higher gas flow rates.
But the payoff is?
The big payoff is a significantly reduced risk of lack of fusion, especially on thicker aluminum, say over 3 millimeter.
Right.
So just to summarize the gas effects quickly, adding CO2 to argon generally gives a hotter arc, deeper penetration, more spatter. Argon oxygen gives a stiffer arc, good for spray. Argon helium gives a hotter arc, higher voltage, and a more fluid pool.
So the right gas mixture is absolutely critical. But even with perfect shielding, how you move the torch, that makes a huge difference too, right? Travel speed and electrode orientation.
Massive difference. The core insight here, faster travel speed reduces your penetration.
Okay, less heat soaking in.
Exactly. Makes your bead narrower, and crucially, it significantly increases the risk of undercut along the edges of the weld.
Not good.
No, it's a really delicate balance. And similarly, your torch angle, how you point it, dramatically affects how the heat and molten metal spread out.
Directly impacts the shape.
Directly influences penetration depth, how much extra metal sits on top, and whether you get that annoying undercut. Mastering it is about visually controlling that weld puddle in real time.
And then there's this subtle one. Contact tip to work distance, or CTWD. Why is this one so interesting?
This is one of those parameters that really separates experienced welders. It's fascinating because of electrical resistance.
Okay.
Here's the surprising insight. CTWD directly influences your welding current.
How?
It's all down to resistive heating and the length of wire sticking out past the contact tip, the stick out. Think of that wire as a resistor.
Right, it heats up.
If you increase the CTWD, make that stick out longer, the wire gets hotter before it even reaches the arc. That increased resistance heating means you need less current from the power source to melt the wire at the set feed speed.
So longer stick out, lower effective current.
Exactly. Which can lead to lack of penetration if you're not careful, especially in tight joints or root passes.
And the opposite, shorter stick out.
Shorter CTWD means less resistive heating, so the power source has to supply more current to melt the wire.
So welders can actually fine-tune the current with this distance.
Experienced ones do it all the time. It's like a hidden adjustment. Longer extensions can also boost deposition rates, get more metal down faster.
But there are limits.
Oh, yeah. For small diameter wires, you need to keep CTWDs relatively short to prevent the wire itself from overheating and causing a poor bead shape. And a caution. Too short a CTWD, especially at high currents, can cause your torch itself to overheat from all the radiated heat.
Makes sense. Are there typical ranges?
Yeah, generally. For dip transfer, maybe 10, 15 millimeter. For spray, longer, like 20, 25 millimeters. And for pulsed, somewhere in between 15, 20 millimeter.
That's a brilliant level of control, almost like a secret handshake among welders, as you said.
It kind of is.
Okay, after CTWD, we have nozzle to work distance and the shielding gas nozzle itself. Quick takeaway here.
It's all about protecting that molten pool. The nozzle to work distance, usually around 12, 15 millimeter, directly affects how well your gas shield works.
Too far and air gets in.
Exactly. You lose that protective blanket, get porosity. And the nozzle diameter, maybe 13 to 22 millimeter, needs to match the size of your weld pool.
Bigger pool, bigger nozzle.
Generally, yeah. Larger nozzles for high current spray transfer, smaller ones for low current dip transfer. And of course, you need to get the gas flow rate right for the nozzle size and gas type to ensure good coverage without causing turbulence.
Okay, and finally for parameters, let's talk inductance. This sounds a bit electrical, a bit mysterious maybe.
It does sound technical, but it's absolutely critical, especially for one mode, dip transfer.
Okay, why dip transfer?
Here's the core insight. Remember how dip transfer works. The wire literally short circuits into the weld pool.
Right, dips in 50, 200 times a second.
When that short circuit happens, the arc voltage basically plummets to near zero. Now, without inductance in the circuit, your power supply would try to instantly ramp up a huge current spike.
Like a dead short.
Exactly. And that massive current spike would cause the wire tip to detach explosively. Think massive spatter, like little fireworks going off constantly. Very messy, poor weld.
So inductance stops that.
Inductance acts like a choke or a damper on how quickly that current can rise during the short circuit. It's an electrical property that creates a magnetic field opposing the rapid current change.
Slows it down.
It slows down the rate of current rise, leading to a much smoother, more controlled detachment of the molten metal droplet. This drastically cuts down spatter and actually increases the time the arc is lit between shorts, allowing for better fusion.
Is there a sweet spot?
Definitely. There's an optimum value. Too little inductance and you still get spatter. Too much, and the current doesn't rise fast enough to cleanly melt the wire off the electrode, tends to stub into the base metal instead of transferring smoothly.
Sounds tricky to set.
It used to be. But thankfully, many modern electronic power sources handle this beautifully, often setting it automatically based on other parameters, giving you a consistently smooth arc.
That's a relief. Okay, so we've laid the groundwork with all these critical parameters: wire speed, voltage, gas, travel, CTWD, inductance. Now, this is where, for me, it gets really interesting.
The transfer modes?
Yes. The different ways molten metal literally, dances from the wire to the workpiece. It's not just one smooth flow.
No, it's a dynamic process. Distinct modes. Dip, spray, pulsed, and globular.
Each with its own rhythm, its own applications, its own challenges.
Exactly. Each suited for different things.
Let's dive into dip transfer first, also called short-circuiting transfer, right?
Correct. The key characteristic here is metal transferring only when the wire dips or short circuits into the weld pool.
How often does that happen?
Incredibly fast. Like we said, 50 to 200 times per second. It's fundamentally a low heat input process.
Low heat, meaning the weld pool isn't super fluid.
Exactly. Relatively cool, not very runny.
So why does that matter? What's it good for?
That low heat input makes it ideal for thin sheet metal, say from about 0.8 millimeter up to maybe 3.2 millimeters thick.
Right, prevents burning through.
Precisely. And it's fantastic for positional welding on thicker sections, like welding vertical up or overhead where you don't want a big fluid puddle dripping down. Also great for root runs in pipe or plate, where you need precise control.
What kind of settings does it use?
Normally uses 100% CO2 or CO2 argon mixtures at relatively low amps and voltages, typically less than 24 volts.
Any downsides? Challenges?
Yeah, process stability and spatter can definitely be issues if your parameters aren't tuned just right. And there's a higher risk of lack of fusion defects if it's not set up or used correctly.
Because of the low heat?
Partly, yes, it requires good technique. And it's generally not used for non-ferrous metals like aluminum.
Okay, so the big advantages.
Low energy means you can weld in all positions, very versatile, great for thin stuff and those critical root passes.
Disadvantages.
Prone to lack of fusion if you're not careful, might not even be allowed for some high-integrity jobs. And it definitely tends to produce more spatter than other modes.
Okay, from dipping. Let's jump to the complete opposite end, maybe. Spray transfer.
Good contrast. Spray transfer is defined by free flight metal transfer.
Free flight.
Meaning the metal detaches from the wire and travels across the arc without short-circuiting. It goes across as a fine, continuous spray of tiny droplets.
Like an atomizer.
Kind of, yeah. And this leads to very low spatter. It's a high heat input, high deposition rate process. Gives you a remarkably smooth, stable arc.
And the key insight here is?
It only happens at high currents and voltages specifically above a certain point called the transition current.
Threshold.
Right. Below that current, you get dip or globular. Above it, the physics change and the metal starts spraying as this fine mist across the arc. Crucially, the arc current is flowing during droplet detachment.
Which means?
Maximum heat, maximum penetration into the base metal.
Where would you typically use this high heat, high deposition mode?
It really shines on thicker materials. Steel's above, say, 6 millimeters thick, and aluminum alloys over 3 millimeter.
Okay.
For steels, though, it's mostly limited to welding flat or horizontal positions or horizontal vertical fillet welds.
Why the limitation?
Because it creates a large, very fluid weld pool. Try to weld vertical or overhead with that, and it'll just drip everywhere. Too hard to control.
Got it. Gas requirement.
Absolutely needs an argon-rich shielding gas to work properly. Can't get spray with 100% CO2.
And here's a cool detail I read. As the current goes up even higher in spray mode, the droplet size actually gets smaller.
That's right, significantly smaller.
Yeah.
And at very high currents, those tiny droplets can even start to spin as they cross the arc. They call it rotating transfer.
Wow. Okay, advantages of spray.
High energy gives excellent fusion. Less chance of defects like lack of fusion. And high rates of weld metal deposition, you can weld faster on thick joints.
And the main drawback.
That big fluid pool. It means it really can't be used effectively for positional welding, at least not on steels.
Okay, so dip for position, spray for flat horizontal speed and penetration. What bridges the gap? Pulse transfer.
Exactly. Pulse transfer is a really clever development. Think of it as taking the best bits of spray transfer, that good fusion, low spatter, free flight transfer, but making it work at lower average currents.
How does that help?
Lower average current means lower overall heat input and a smaller, more controllable weld pool. And that gives you positional welding capability, even for steels.
So spray quality, but usable out of position.
Precisely. It's still free flight droplet transfer, no short circuiting across its whole working range. Very low spatter, less heat input than regular spray, and a much lower risk of lack of fusion compared to dip transfer.
How does it actually work? What's the mechanism?
It's fascinating. It basically extends spray transfer down to lower average currents, maybe 50 to 150 amps, by pulsing the current rapidly.
Pulsing.
Yeah. You have a low background current, maybe 20 to 80 amps, which just keeps the arc alive, keeps things ionized.
Okay, just ticking over.
Right. Then the machine superimposes high-frequency pulses of high current on top of that. Each pulse is strong enough above that transition level we talked about to detach a single, precisely controlled droplet of metal and send it across the arc gap.
1 drop per pulse.
Ideally, yes. And this happens fast, maybe 50 to 300 pulses every second.
Incredible control. So where is this used?
It's excellent for positional welding of steels, typically thicker than 6 millimeters, but it's so controllable you can even use it on thinner sheet steel, down to maybe 1 millimeter.
Versatile.
Very. And a big advantage for aluminum welding is that it lets you use larger diameter wires, which are generally cheaper and much easier to feed reliably through the torch liner, even on thinner aluminum plates.
Right, avoids those wire feeding issues. So, advantage is clear. Good fusion, low spatter, small pool for all position welding. What about disadvantages?
Traditionally, the main ones were cost and complexity. The power sources are more sophisticated and thus more expensive.
And setup. Must be tricky with background current, pulse current, frequency.
It used to be difficult. Setting all those parameters individually was a real challenge, but modern synergic systems have largely solved that.
Synergic.
Yeah, it means the machine has pre-programmed relationships built in. You tell it the material type, wire diameter, and gas you're using.
And it figures out the pulse parameters.
Exactly. Often you just adjust the wire feed speed with one knob, and the machine automatically sets the complex pulse parameters for optimal transfer. Made setup much, much easier.
That's a huge step forward.
Okay.
One more transfer mode to cover briefly. Globular transfer.
Globular, often seen as the ugly duckling of transfer modes.
Oh, that.
Because it's inherently unstable and irregular, you get these large molten droplets forming on the end of the wire, often several times the wire diameter.
Big blobs.
Big blobs. And they eventually detach mainly due to gravity when their weight overcomes the surface tension holding them there.
Sounds messy.
It often is. It's characterized by that irregular transfer, medium heat input and deposition rates, but a definite risk of spatter. The arc itself tends to be unstable and can wander around. It's generally not widely used, especially in places like the UK, precisely because of this instability.
Not a preferred mode, then.
Not usually, no. Well, you can sometimes use it for, say, mechanized welding of medium thickness steel, maybe 3 to 6 millimeters, but only in the flat position.
Okay.
And often you have to use techniques like a very short arc length, almost burying the arc in the puddle, just to try and minimize the spatter.
So the disadvantages are pretty significant.
Yeah, it's frequently associated with problems like lack of penetration, fusion defects, and just generally uneven, unattractive weld beads because the transfer is so irregular and unpredictable. Best avoided if possible.
Right. Okay, so we've explored the individual parameters, voltage, wire speed, gas, inductance, and then these distinct ways the metal transfers. Dip, spray, pulsed, globular.
Yeah, the whole toolkit.
Now, bringing it all together, it's clear how, say, specific voltage ranges and argon-rich gases are essential for spray transfer, or how inductance is the key enabler for stable dip transfer.
They're all interconnected.
Which raises that crucial question. Why is it so important for welders, or even people managing welding operations, to really understand these different modes and their parameters? Not just know they exist, but understand the why.
The core insight, I think, is that this understanding gives you immediate diagnostic power and ultimately control.
Control over the outcome.
Absolutely. Knowing these details isn't just about following a chart or a procedure. It's about being able to look at a weld or listen to the arc and diagnose what's going wrong or how to optimize it.
Like troubleshooting in real time.
Exactly. Optimize the process for peak efficiency, minimize waste, and truly control the quality of the final joint. It's where the art meets the science behind that seemingly simple arc.
So it helps avoid common problems.
Definitely. Understanding the links helps minimize common defects like lack of fusion, always a concern in dip transfer if it's not managed perfectly, or porosity from losing your gas shield, or accidentally burning through thin material because you drifted into the wrong higher heat transfer mode.
It's the difference between a good weld and a bad one, fundamentally.
It really is. Quality, efficiency, safety, it all ties back to controlling these fundamentals.
Well, we've certainly taken a deep dive today into this fascinating world of MIG-MAG welding parameters and that incredible dance of metal transfer modes.
It's a complex dance.
It is. From the subtle art of setting voltage in CTWD to the critical role of shielding gases and that precise control inductance offers in dip transfer. Hopefully, you now have a shortcut to being truly well-informed about the core mechanics of this vital process.
Yeah, and this understanding, it really reveals how every single adjustment, every choice of gas or setting fundamentally changes that interaction right there at the arc.
It's physics in action.
Totally. And if you connect that to the bigger picture, it highlights how these seemingly small technical details can have profound impacts on the safety, the strength, the efficiency of engineered structures all around us.
Things we rely on every day.
From the cars and trains we travel in, to the bridges we cross, the buildings we live and work in. It's everywhere.
So maybe as you go about your day, here's a thought to leave you with. How many other seemingly simple processes around us are actually governed by such intricate, finely tuned parameters? And what hidden transfer modes, so to speak, might be at play in the complex systems you interact with every single day?
That's a great question. There's often more going on beneath the surface than we realize.